The shocking world is officially the farthest human-produced object in space. More than for decades ago, the spacecraft began its journey through the vastness of space. There existed, prior to the Big Bang, gravity waves that we will detect from the occurrence of creation. Data collection and prior access were limited to things that have just taken a terrifying turn. Physicist Michio Kaku has just announced that there has been a terrifying finding. Voyager 1 has sent a new communication to Earth, and it's something that nobody anticipated. Join us as we discover what the terrifying message was and how it might just change everything. Michio Kaku is a world-renowned futurist and theoretical physicist who has contributed significantly to our understanding of the universe. His work in physics, also established by Kaku himself as a best-selling author, is widely recognized. He writes about science's future, the complexity of the human mind, and the human condition, but space exploration is something he's particularly passionate about, and he has published numerous books on the subject. One of his most popular works is definitely The God Equation, The Quest for a Theory of Everything. In this book, he delves deeply into the enticing concept of a theory of everything in physics, a complex and elusive system that aims to bring together all basic forces and accurately describe each individual's behavior in the universe's fundamental material. Kaku's investigation focuses on the idea that this theory, which is frequently referred to as the God Equation, has the potential to shed light on the universe's darkest secrets and provide a profound understanding of the environment. Throughout the book, Kaku traces the historical progression of theories of unity. From Newton's law of universal gravitation to Einstein's theory of relativity, quantum mechanics, and beyond. These milestones reflect humanity's persistent pursuit of a deeper comprehension of the foundational forces that govern the universe. In the quest for a grand unified theory that aims to unify the electromagnetic, strong, and weak nuclear forces, Kaku investigates various strategies and theories. String theory is one of the most prominent contenders. At its core, string theory proposes that the fundamental constituents of the universe are not made up of point-like particles, but tiny, one-dimensional vibrating strings. These strings can oscillate at different frequencies, much like the various notes produced by a violin string. Each frequency corresponds to a distinct particle, like electrons, quarks, or photons, and the interactions among these particles determine the behavior and properties of matter and forces. As if the universe were a single instrument and all strings must perform their duties for everything to function precisely. One of the interesting features of string theory is its ability to incorporate both quantum mechanics and general relativity. Quantum mechanics describes the behavior of matter at the smallest scales, while general relativity explains gravitational interactions at the cosmic scale. However, these two theories have been notoriously difficult to reconcile. String theory attempts to bridge this gap by providing a consistent framework that unites these seemingly disparate theories. The vibrations in string theory's strings may appear in various forms, including particles with distinct properties, allowing for a description of natures for fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces. Not only that, but string theory also proposes additional spatial dimensions beyond the familiar 3 dimensions of space and 1 dimension of time. These extra dimensions, hidden from our everyday perception, are crucial in influencing how strings behave and the particles that result. These additional dimensions provide an explanation for why gravity appears significantly less powerful than the other forces, as it may be diluted across these other dimensions. But Michio Kaku isn't a man who only looks at one aspect of subjects. He also investigates the profound effects of the theory of everything all around him, discussions in which he explores the possibility that a theory of this kind could provide insight into the characteristics of black holes, revealing their interiors, which remain a mystery to the outside world of science. Scientists have been asking questions for a number of decades, and there's also the concept of time travel and the existence of other universes that could be investigated within the framework of a comprehensive theory. However, in all of that, he does not depart from philosophical or existential concerns brought up by the concept of an all-encompassing theory. Kaku investigates whether a theory might provide insight into the existence of a divine creator or offer a greater comprehension of the intricate inner workings of the universe itself. Investigating these important questions adds an interesting dimension to the need to look for a scientifically unifying theory. This theory not only provides an extensive summary of the background of unified theory, but also inspires readers to consider the profound questions that arise from our search for a theory of everything. The pursuit of a unified theory by Einstein was primarily concerned with the fusion of gravity, electromagnetism, and the strong and weak nuclear forces into a single equation. He famously aimed to learn more about the mind of God by deciphering the underlying guiding principles for the universe. Einstein's approach was rooted in his belief that nature's laws should possess a simple and elegant mathematical structure. In contrast, Kaku's concept of the God equation takes inspiration from Einstein's original concept but expands it to include changes that have occurred since Einstein's time by introducing string theory. The God equation, as defined by Kaku, accommodates the possibility of unifying not just the basic forces, but also a more in-depth comprehension of the universe as a whole. One of the best ways to achieve this is by looking at real data provided by probes that enter the system. Space is a shocking location. Voyager 1, launched by NASA on September 5, 1977, occupies a remarkable position in space exploration history alongside its twin spacecraft, Voyager 2. Voyager 1 set out on an extraordinary endeavor to investigate the farthest points of our solar system and beyond, providing invaluable insights and scientific advancements along the way. Originally designed to study the giant planets Saturn and Jupiter, Voyager 1 has far surpassed its initial objectives. In its interactions with these gas giants, the spacecraft captured breathtaking images and collected a wealth of data that revolutionized our understanding of these distant worlds. Voyager 1 revealed the intricate aspects of Jupiter's turbulent atmosphere, including the iconic Great Red Spot, as well as the complex ring systems and enigmatic moons of Saturn, like Titan, which has a thick atmosphere and intriguing hydrocarbon lakes. Beyond its encounters with Jupiter and Saturn, Voyager 1 continued its journey into the outer solar system, venturing into uncharted territory. It revealed new information about the planets in outer space, despite not having close flyby encounters with these celestial bodies. The spacecraft's instruments, including the plasma wave system, magnetometer, cosmic ray subsystem, and ultraviolet spectrometer, provided important information about the magnetic fields, plasma composition, and environments of these distant worlds. Despite being more than 14 billion miles away from Earth, Voyager 1 continues to maintain an impressive line of communication with us. This is made possible by employing a high-gain antenna, an essential part of the spacecraft's communication system. The antenna serves as Voyager 1's primary lifeline, enabling it to send scientific data back to Earth and receive instructions from mission control. However, the antenna cannot function on its own. The pursuit of a theory of everything in physics aims to unify all fundamental forces and describe the behavior of matter in a single framework. String theory is one of the most popular candidates for a TOE, proposing that the basic components of the universe are not particles but tiny, vibrating strings. These strings vibrate at various frequencies, giving rise to different particles. String theory attempts to reconcile quantum mechanics and general relativity to fundamental theories that explain the behavior of matter and gravity, respectively. The implications of achieving a TOE are profound. It could unlock deep insights into the universe's nature and provide solutions to persistent questions in physics, such as the behavior of black holes.